We continue with Chapter 7, Operators and Invariant Subspaces. In this chapter, F will be an arbitrary scalar field, although there are some special cases for some special scalar fields. And also V will be a general vector space over the scalar field F. V is mostly finite dimensional, but we will also work with infinite dimensional cases as much as possible. Let me remind you that the notation T is a linear operator from V to V. The book right now omits the word linear operator, but of course we cannot do much with nonlinear ones. So in all cases, T will be a linear mapping from V to V, and this is called operator when both the domain and the codomain are in the same vector space V. And the main topic is to find T-invariant subspaces U1, UR, such that we can reconstruct the space V as a direct sum of these T-invariant subspaces. So I would like to remind you to the direct sum notation. Also, T-invariant subspace means each of these subspaces, when you apply the linear operator, they stay inside this linear subspace. This is the property, for example, what projections had. Except projections also had some simpler properties where actually it was the identity on the UI subspaces. The reason why this is interesting for us is because with this tool, with these T-invariant subspaces, we can actually split the operator into parts. So what we do is we define with Ti the restriction of T to vector space or subspaces Ui. This operator is now from Ui to Ui because we just change the domain. We just restrict the domain to Ui. And then we write T as a direct sum of these operators. Although this is a little bit misleading definition, so note please that what the direct sum means is that for all V vector in the vector space, V can be written as U1 plus UR. That's because of the direct sum, and actually this sum is also unique. This representation is unique. So what we mean by this sum operators is that when you want to apply T to V, it doesn't make sense to write this as T1V because V is not in the domain of Ti or T1. So the way we define this sum when we apply it to V, since V has this sum form, T1 will be applied to U1 only because that's the only thing that's in the domain of T1. And similarly, TR is applied to the UR part of V. The reason why this is important in application, because if you have these subspaces, for example, U1 and U2 in a vector space, let me remind you that all these subspaces are supposed to have the zero vector in them. Then the V space and the mapping might be complicated, the T mapping or T operator from V space to the V space, but with this sum of the operators or splitting the operator into a sum, what we have is just from U1 to U1, the T1 operator, which is usually much simpler, and then we also have the from U2 to U2 subspaces, the T2 operator. So the idea would be that this is simpler than T. Also sometimes U1, U2, some of these subspaces UR subspaces are more important than the others. The first section of this chapter is actually Eigenvalues and Eigenvectors, which is a popular topic in the undergraduate linear algebra course, and we will review the basics. We need some material, especially for the theoretical part, from chapter 6 about determinants. First of all, we have to define the characteristic polynomial, and this is in 6.3.8. The characteristic polynomial of a linear map or a linear operator T in LV, where V is finite dimensional, is defined as C sub t of x. C stands for the characteristic, the initial of the characteristic polynomial. Sometimes P is used for that. And it's the determinant xi minus the matrix representation of t in a basis B, where B is a basis in V, as I mentioned. Sometimes the characteristic polynomial is defined by interchanging the order of these two terms, which means that then there is a change in plus minus sign. Some basic properties of this characteristic polynomial of a linear operator. First of all, Ct of x, this polynomial, is independent of B, of the basis. Also, it's a so-called monic polynomial, which means that the leading coefficient is 1. And chapter 6 actually works a lot with this characteristic polynomial. It has a form like this, C sub t of x, x to the n plus a1, x to the n minus 1 plus a2, x to the n minus 2. So decreasing powers of x all the way to a sub n minus 1 times x, which is x to the 1, and then a constant term an. And then the first term is x to the n. The leading order term has coefficient 1. There are very important theorems that we will not prove here. There are several different proofs. The so-called Cayley-Hamilton theorem states that if you take the characteristic polynomial and replace x with t, then you also get 0, which is the 0 operator. Perhaps as a student, it's very simple to just substitute t for x and say that, well, if c of x is 0, then c of t is 0. It's just a different variable. But please note that while x is a variable, t is an operator. And ct of t is this operator polynomial, t to the n plus 1 times t to the n minus 1, and then 8 sub n minus 1 times t. The constant term, an, doesn't make much sense to add to an operator. So the way we add it is that we multiply it with the identity operator. And this is supposed to be the 0 operator. Also note that power of t, for example, t squared is just t applied twice, t circle t. T cube is t applied 3 times, one after the other on a vector. And since we talked about the matrix representation of the operator, when we look at matrix representation A in some basis, if the dimension of V is n, then A is a n by n matrix. And then another way to write this is that the characteristic polynomial of this matrix, when we substitute the matrix A, is a to the n plus a1 times a to the n minus 1 plus an minus 1 times a plus an times the identity matrix. And then, of course, it's much easier to talk about the power of a matrix because it's just multiplication of the matrix by itself. So these are kind of preliminaries that we will have to use at some point. Going back to invariant subspaces of T operator, linear operator, we had before that the 0 vector itself is a trivial subspace, and T of 0 for a linear operator is 0, so that means it's invariant. Also, V is invariant since T of V is a subspace of V. By definition, T is a mapping from V to B. So we have already 2 invariant subspaces. Some other invariant subspaces are the null of T is invariant. Also, the image of T is invariant. We looked at these properties also before. These 4 invariant subspaces are usually called trivial, and we don't work much with these because these are obvious invariant subspaces. So we are more interested in other invariant subspaces. And we start with one-dimensional T-invariant subspaces. So these are subspaces U, and what we have is that TU is a subset of U. And the dimension of U is 1. If the dimension of U is 1, that means it has a basis with one non-zero vector. So that means that U equals to the span of some vector. Let me denote it with U tilde. And then this U tilde vector is not the zero vector. What this means is that U equals to scalar multiples B times U of this vector, where B is from the scalar field. So if U is T invariant, that means for any vector V from this space U, we have that TV is also in this U subspace. Since TV is in U, that means this TV element is also the scalar multiple of this U tilde for some B from the scalar field. So this B might change. It might be different for different V vector. Now let's choose this U tilde vector, the basis vector actually. Then we also have this, for this U tilde vector, that its image, T U tilde, is scalar multiple of U tilde. And now let me denote this scalar specific to the U tilde as lambda. This is for some lambda from the scalar field. So using this notation, then in general, if you have V vector in this invariant subspace U, V can be written as a scalar multiple of U tilde, since U tilde is a basis, one element basis. And then when we apply the linear operator to this B times U tilde, since it's a linear operator, we can factor out the B scalar. Then for U tilde image, we already used the lambda notation. So now we have two scalars, B and lambda. The scalar multiplication can be rearranged. So we can write lambda times B times U tilde, and B times U tilde was V. So we get that this is lambda times V. What we get with this, that if U is a one-dimensional T invariant subspace with T of U tilde equals lambda U tilde for a basis with one vector U tilde and a lambda from the scalar field, then for all vector from this one-dimensional subspace, actually TV is the same as lambda times V. So the fantastic thing about this, about the one-dimensional T invariant subspace, that T is just a multiplication on this subspace U. So that's the huge thing, that it turns out that when you look at one-dimensional T invariant subspaces, on those the linear operator is just a scalar multiplication, which is very simple. Think about, for example, differentiation and integration and other complicated linear transformations we looked at before. They all can be reduced to a scalar multiplication on one-dimensional T invariant subspaces. So this gives us the definition of eigenvalues. If lambda from the field F has the property that T of V equals to lambda V for some non-zero vector V, then this lambda is called an eigenvalue of T. A vector V from this vector space V is called an eigenvector of T belonging to eigenvalue lambda if T of V equals to lambda V. That is, if you rearrange this, what we get is that T minus, if you rearrange this and factor out V, since T is linear, then what we get is a T minus lambda I V equals to 0. So this is the definition of the eigenvalue and eigenvector. Note, for eigenvalue, we use non-zero vector V, because for zero vector, this is always true, so that T0 equals to lambda 0 for any lambda, since this is just the zero vector. So that doesn't make sense to talk about eigenvectors if you use the zero vector. For the definition of an eigenvalue, all lambda would be eigenvalue in this case. That's why we needed non-zero vector. But for eigenvector, we allow zero eigenvector. Once we have an eigenvalue, 0 will be always an eigenvector. So the reason for this is because, and some books restrict the eigenvectors not to be 0. Still, we should call this trivial eigenvector. And when you are looking for eigenvectors in the homework assignments, of course, we never look for 0 eigenvector. But the reason why this is so nice is because looking at this definition for the eigenvector, that means that the set of eigenvectors is actually the same as the null space of this t minus lambda I operator, which is actually then an eigenspace, since it's a subspace. And then also this is a t-invariant subspace. So again, the picture is that we have these subspaces, U1, U2, if it's higher dimensional than other subspaces, U3, in V. In the middle, each of these subspaces contains the zero vector, of course. And then what we have is that if you restrict the T operator to these invariant subspaces, then the effect is just simply some kind of scalar multiplication. So of course we can have different eigenvalues. What's also important to note is that unless you consider the zero vectors, then different eigenvalues have different eigenvectors, and more precisely, they are linearly independent. So the theorem says that non-zero eigenvectors corresponding to distinct eigenvalues form a linearly independent list. So the way we write this mathematically, that let T be a linear operator and lambda 1, lambda m are distinct eigenvalues of T with corresponding non-zero eigenvectors v1, vm. Then the list v1, vm is linearly independent. Let's see the proof of this theorem. This is proof by contradiction. So we suppose that the list is linearly dependent. Proof by contradiction. So we had a linear dependence lemma before that says that there is a j index, which is the smallest, which is already linearly dependent from 1 to j. So there is a smallest index j such that v1, vj is linearly dependent, but the previous ones are linearly independent. That's why it's smallest. So j minus 1 is all linearly independent. And also linearly dependent means that this vj is actually in the span of the previous ones. That was another important part of the linear dependence lemma. So from this, that vj is in the span of the previous ones, what we have is that then vj is some kind of scalar combination, linear combination of these previous elements, I going from 1 to j minus 1. Then we apply t to both sides, and since t is linear, we can take it inside the sum, and we can also factor out the scalar multipliers. So what we get is the sum as I goes from 1 to j minus 1, ai t of vi. And since these are eigenvectors, we get that t of vj is lambda sub j times vj, and also t vi's are lambda I times vi. Now looking at this and looking at the original linear combination that gives v sub j, there is a similarity. The left-hand side just has a lambda j multiplier in the second case. So let's multiply both sides now in this equation with lambda j. Then on the left-hand side we get lambda j times the vj vector, and on the right-hand side it's almost the same sum. The big difference is that lambda, instead of lambda i's changing with the I index, we have just lambda j. So the big difference now between these two is that one has lambda I changing with the I index, the other one has just lambda j multiplier. And then we can subtract these two equations. So on the left hand side we get the zero vector, and on the right hand side we can collect like terms and factor out ai vi, and then what we are left with is lambda I minus lambda j. Let me write this out term by term, although it just maybe helps us to see better what's going on. The last one is a sub j minus 1 lambda j minus 1 minus lambda j, v sub j minus 1. But what we had is that the v1, j minus 1, or list is linearly independent, because the V1 Vj was the smallest one that was still linearly dependent. So we cut down the large, possibly very large V1 Vm linearly dependent list to the smallest possible V1 Vj, and now the smaller one, any smaller one, would be linearly independent list. But then since we have the linear combination, and what we have is that V1 Vj minus 1 list is linearly independent, all the coefficients must be 0, since these were distinct eigenvalues. So this is not 0, this is not 0, but the coefficients should be 0, since for linearly independent list, only the trivial linear combination can give the 0 vector. So the coefficients must be 0. What we have is that ai times lambda I minus lambda j equals 0, I going from 1 to j minus 1. And since this is not 0, that means that ai must be 0, as I goes from 1 to j minus 1. But then that means, going back to this linear combination of the elements, that means that the Vj vector is a 0 vector, which is a contradiction, since we started saying that these V's are non-zero eigenvectors. But using the assumption that they are linearly dependent, we obtain a contradiction that one of them is 0 vector, so hence they must be all linearly independent. So V1 Vm is linearly independent. Then this is a corollary. If the dimension of the vector space is n, and this is a finite dimension, no linear operator can have more than n distinct eigenvalues, since otherwise there would be more than n linearly independent eigenvectors, which is impossible in the n-dimensional vector space. So before we continue with theoretical parts, at least one example.